back in May at Battelle at the the conference on chlorinated and recalcitrant compounds remediation. And so she had a bigger room, probably a little more sweaty palms. This is kind of a nice, comfortable group here. We're going to talk today about enhanced in situ bioremediation. We're going to give a primer. Oh, what does that mean? What's the approach? And then give a specific case study, which is kind of one of the hardest sites that we've had to tackle, highest concentration chlorinated solvent site, and how we've applied bioremediation to that, and then subsequently enhanced it for improved degradation. And I'll just launch in. Let's see. Okay, real quick about Landau Associates. We're about 150 people, mostly here in the Northwest, but about a year ago we added 10 people in Baton Rouge that do specifically air modeling, air permitting for all the petrochemical folks down in that region. Erin and I are both, and Alyssa also, and Bill, and who else was on here? Adriana. We're part of the environmental remediation group. We're about 45 people strong that do, your typical site investigation, and then RIFS, cleanup action plan, and then actual design and implementation and cleanup. I think something that maybe sets us apart a little bit from other companies is we very commonly take it all the way through to cleanup design and implementation, and we do a lot of our own cleanup implementation, particularly when it comes to bioremediation. We do our own injections. And then we have these other sort of complementary and adjacent services. So I've been doing bioremediation for about 24 years now, and over that period of time, we've designed and implemented bioremediation on, I think it's like 56 or 57 projects, and about a little over half of that are chlorinated solvents, which will be a primary focus of our discussion today. We do our own injections. We intend to do fairly large volume injections, 2 wells, and we have a crew and injection gear to go out and implement that. Over 4 million gallons injected, that adds up pretty quick. And that sort of field experience, I think, really informs us in our design and also in like our feasibility study evaluation of what might work, because we've been out there when it hasn't worked, and we know what doesn't work, and what the real life constraints can be. So the talk today, I want to start out with this primer, just kind of give the background and the baseline for what is in situ bio, and then get into case study, and hope to have around 15 minutes at the end for questions and answers. So as we go along, if you have a quick question, please shout out. I'm not sure if I'll see raised hands. I might, but shout out. If it's a longer question, if you can just hold it to the end, and we can circle back to whatever slide might pertain to that question. So I would ask, and maybe you can do this by a reaction, give me a thumbs up or a smiley face or something. Have you been involved in a bioremediation project, an a groundwater or aquifer bioremediation project? All right. I see a couple. All Landau people so far. And then maybe I can get another, response. Was it successful, or was it a failure? I know those are kind of broad strokes questions. Success or failure? Crickets. And I asked that question because the devil is really in the details, and we'll see some of that in the presentation today. Often it will be like, oh, we applied bio at this site, but when you get really right down to it, it's like it really wasn't done correctly, or what was injected wasn't enough, or it wasn't the right substrates, or the well spacing was much too far apart, the volumes were too small. And just like anything else in engineering or science, it's got to be done right to be effective. So launching into the primer, what is bioremediation? It's really just taking advantage of this natural system where all these bacteria are down in the aquifer. They're in the nooks and crannies where these contaminants exist. And if we will properly stimulate these bacteria, they can get at and degrade this contaminant mass that is so difficult for us to get to. We'll talk about some, comparative technologies that we often would apply to cleanups of petroleum or chlorinated solvents that for many reasons don't work as well as an in situ treatment. And these are all different forms of dechlorinating bacteria degrade chlorinated solvents like PCE, TCE, carbon tetrachloride, chloroform, probably all compounds you guys have heard of, and these tend to be dry cleaning solvents. And on a larger scale, they are commonly used industrial degreasers. And so after petroleum, chlorinated solvents, the family of chlorinated solvents is the most widely used and released, contaminant in the United States and probably across the world, just very widely used. And this bacteria here in the top center, that's the Dehalococoides bacteria, and we'll talk a little bit more about that it has a special role, an essential role in degradation of chlorinated ethines like PCE and TCE. The great thing is about these bacteria when it comes to chlorinated solvents is we just have to feed them. They're there. They're mostly ubiquitous in the natural environment. We just have to give them some food. So this is a list of applicable contaminants. If you went back 30 years or 20 to 30 years ago, there was a real question whether it would be effective for chlorinated solvents. They're highly toxic and they have very low cleanup levels. At that point, it was pretty clear that it worked for petroleum if you did it right. But certainly for chlorinated solvents and explosives and propellants, that understanding that yes, bioremediation can be effective has evolved to the point it's no longer real innovative. It's like pretty established that it works. And yes, bioremediation works for all of these contaminants here. There's another kind of longer, another adjacent list where there are these other contaminants where yes, bioremediation could work. It's a little more innovative. It's maybe a little more challenging. It may be a little more specific to what your site conditions are and what site constraints are. PCBs, for example, yes, it can biodegrade, but it still biodegrades down to some other PCBs, so it may not be highly effective. Radionuclides can become insoluble through biodegradation, but they can still resolubilize over time without some very specific actions and precautions. So this is just a list to where it won't be quite as simple. So when we talk about biodegradation, what we're talking about is bacteria obtaining energy from the degradation reaction. It's a direct metabolism. And so it's lunchtime. You guys are probably all have some lunch in front of you. You're about to metabolize your turkey sandwich, and you're able to do that because you're breathing oxygen. So oxygen is the electron acceptor for us as humans, and then we eat food, which becomes the electron donor. Well, it works in a similar way with bacteria, except that bacteria, yes, there are bacteria that can utilize oxygen as the electron acceptor, but there are other groups of bacteria that can also use things like nitrate and sulfate and carbon dioxide, and some of our contaminants like TCE as the electron acceptor. They can essentially respire it or breathe it. And then for those kind of contaminants, we provide the food or the electron donor in the forms of things like, anything that can ferment and ultimately ferment down to hydrogen. And it's direct metabolism because they obtain energy, and then there's sort of waste and end products that we watch for to make a demonstration that it is actually occurring as intended. So I have kind of one slide here about petroleum and petroleum type compounds, and then we'll focus mostly on chlorinated solvents going forward. But I want to just make the point that when it comes to trying to treat petroleum, we can provide oxygen as the electron acceptor, or we can provide these other electron acceptors, nitrate and sulfate, to stimulate anaerobic biodegradation. And that's less well understood. I think most people understand that petroleum degrades under aerobic conditions, but it also degrades very well under anaerobic conditions. And that's in the literature is maybe just not as well understood. We find that it's important to take an anaerobic approach at many of our Pacific Northwest sites where the aquifer is naturally anaerobic. And that's many sites that are along the shoreline where maybe it was a mudflat depositional environment, and then there's fill over the top. And so to try and take an aerobic approach there is very counterproductive. Okay, so the kind of contaminants that we provide electron donor for then are the chlorinated solvents, and things like chromium-6, where when you take a bioremediation approach, you convert that hexavalent chromium, the soluble chromium, to chromium-3, which is insoluble. And you can also take nitrate and degrade it ultimately to nitrogen gas. And nitrate in some places is a contaminant in many agricultural settings. And when we think about what donor to apply, there's two major groupings: soluble, which is fast release, quickly consumed, and insoluble, or low solubility, which is more slowly consumed. And here's groupings of the usual suspects that we would use. There's advantages to both. Soluble moves further down gradient from where we inject it, so you get a larger treatment area, but it's used up more quickly, and so you have to inject it more frequently. Also tends to have low pH concerns in a bigger way than the slow release donors. Slow release donors like vegetable oil tend to they definitely last longer. I mean, they could last 3 years where you've injected them, whereas the sugars might last 4 months, 5 months, 6 months. But it doesn't travel as far down gradient. So we've found over the years that a combination of the two really allows you to benefit from the strengths of both electron donors. And I showed TPH on here as an insoluble. Sometimes you'll have sites where you have mixed petroleum, which is an electron donor, and mixed with chlorinated solvents, which is an electron acceptor. And that can be sort of a happy situation if you recognize it and can understand it and demonstrate that these co-contaminants are serving to degrade each other. And when we inject donor, often we do it in very large quantities. We've had some injection events where we've injected hundreds of thousands of gallons at a time of dilute injection fluid, and have had 3 or 4 or 5 tanker loads, 5,000-gallon tanker loads of vegetable oil that we would dilute into that injection fluid. Well, that was out of sequence a little bit, but what we're talking about with chlorinated solvent biodegradation is a sequential reductive dechlorination. PC and TCE are what was released. Those are the parent products, and as they biodegrade, they are converted to cis DCE and vinyl chloride. So PCE is perchloroethylene. It has 4 chlorides: trichloroethylene 3, DCE2, vinyl chloride 1. And it's the chloride ion that makes these compounds toxic. Once you have knocked off the last chloride ion, once you convert vinyl chloride to ethene and ethane, those are non-toxic end products. And ultimately, they're degraded, mineralized to carbon dioxide and water. Ethene is the gas that comes off your banana as it ripens, for example, for context. Now, the difficult step here is from cis to vinyl chloride, and there's a few reasons why sometimes we would get it so commonly stops at cis DCE that it's commonly known as cis stall or DCE stall. And it can happen because you don't have the right bacteria. There's just one bacteria that mediates this specific step, whereas all the other steps are mediated by a number of commonly occurring bacteria. Or your aquifer redox is not reduced enough for this to degrade, or your pH is out of the optimal range. Either they're too low or too high. Now, so that's an intro to that. We'll talk about some of these cis stall concerns as we move through the presentation. So here's that redox. I think everybody is familiar. Everybody who comes from a science background is familiar with this idea of aerobic or anaerobic. Or it's aerobic if there's oxygen. It's anaerobic if there's not oxygen or dissolved oxygen in the groundwater. But to do bioremediation, we need to understand more specifically, is it just a little bit anaerobic or is it highly anaerobic, sort of sulfate reducing and methanogenic? These are all electron acceptors. These are naturally occurring electron acceptors in aquifers. They're sequentially degraded in this order because bacteria get more energy from nitrate and less from carbon dioxide. So carbon dioxide doesn't get degraded till all these other things are mostly consumed, and bacteria have to move on to their least favorite sort of electron acceptors. And this is really important for understanding chlorinated solvent biodegradation because PC and TCE can degrade to DCE under sort of moderately reducing conditions. I need to go back here. Sort of iron reducing conditions, you will get cis DCE, but you won't get to vinyl chloride or to ethene unless you're highly reducing, sulfate reducing to methanogenic. And we monitor that through groundwater parameters, and we can understand, like, yes, we've converted the aquifer fully over to methanogenic conditions, or we haven't. We can watch for the end products and monitor that it's occurred. So probably a lot of you are familiar with sort of the site cleanup feasibility study, where you consider the whole host of technologies and which technology is most appropriate for your contaminant and for your site and for your objectives. And I'll run through just like a 3-minute sort of feasibility study analysis of what kind of technologies we could apply to chlorinated solvents, particularly in a high concentration source zone. And there's in situ bioremediation, which we're going to talk about. And there's in situ chemox, which is sort of the opposite of taking an anaerobic bioremediation approach. Instead, we're adding chemical oxidants like permanganate, persulfate. And then there is in situ chemical reduction, which is anaerobic reductions, but they are chemical, not biological. And I imagine this group has heard of zero-valent iron and maybe polysulfide and iron sulfides that mediate this chemical degradation of chlorinateds. And then you can also heat the aquifer zone, the source zone where the contaminants are at high concentrations, and you can do that with steam or conductive heating, which is like a water heater down inside a well, or electrical resistance heating where you pass electrical current through the aquifer material and achieve heating. And those are primary things that you would apply to high concentration chlorinated solvent source zones. There's also solvent flushing, which doesn't work great, but the idea is you pass a solvent through this high concentration area that will dissolve the TCE, and then you collect the solvent and dispose of it. But it doesn't work very well. There's also injected activated carbon, where there's powdered activated carbon. You guys have probably heard of things like plume stop, where that's just a absorptive thing, and that may have some application to down gradient, low concentration ends of plumes, but not to source zones, just because it's absorptive and the absorptive capacity is quickly exceeded. Pump and treat used to be the go-to technology for all sorts of sites, including petroleum and chlorinated solvents, and it's become very clear, even going back probably 30 years ago, 25, 30 years ago, it was really starting to be understood that, well, it doesn't work for mass removal. So it's kind of like if you pump out groundwater and treat the groundwater around a chlorinated solvent plume or a source, really you're just mopping up around the edges. You're not really doing much for mass reduction. And there's reasons for that. A lot of the mass is tied up in the aquifer matrix, not available in the aqueous phase. If it was all in the aqueous phase, yeah, maybe you could just pump out a few pore volumes of water and be clean. But most of the mass, 70% of the mass, is in the aquifer matrix, not the pore water. So bioremediation for sources compares very favorably to these other technologies when it comes to effectiveness and cost and longevity. And we'll talk about each of these a little bit. This was a really interesting paper back in 2005 where they looked at, and you can see the N here for the number of each of these categories of sites. So 6 thermal, 6 solvent, 13 chemical oxidation, and 11 bioremediation sites, where they looked at cost to treat source zones. And we have median cost and in these whisker plots, max min costs. And the takeaway is, whether we're talking about maximum minimum or the median cost, bioremediation does better than these other alternatives. And Landau Associates tends to be on our projects, towards the low end of the median or a little bit below the median at maybe $20 a cubic yard. Of course, the larger the site is, the more your kind of cost per aquifer volume tends to go down.
Hey, Clint, is that
yes?
Quick question on that price chart there? Is that for all contaminants of concern, or just chlorinateds, or?
This is specific to chlorinateds.
Okay, thanks.
Thank you. Bioremediation has, and specifically when we're talking about bioremediation of chlorinated solvents, it has this additional benefit over in situ chemox or heating, for example, that it has persistent treatment that will continue to lower your concentrations and mass after you stop active treatment. And there's a couple of primary reasons for that. When we inject this food to this bacteria, we grow up these huge populations of native bacteria, and then at some point we stop injecting the food anymore, and those bacteria die. And as they die, there's recycling that occurs. They become their own food source for the continuing dechlorination. And there's also electron donor that as we inject it, it finds its way through diffusion into sort of dead end pore spaces in the aquifer, and then that becomes a storage that that comes back into the preferential flow zones in the years that follow. And there's a number of really good papers about this, and we've seen this on our sites also, that you can have very good treatment occur, 5 to 10 years after you do your last injection. Now, commonly you don't get that if you do one injection, but if you do 3 injections, say, of food, of electron donor, you can expect a pretty sustained treatment period to follow. And that can be a really great benefit because, you think about treatment trains, we're going to apply bioremediation actively, and it's expensive for this period, and we're going to see a 3 order of magnitude concentration reduction, and we're maybe not quite at our cleanup level. We need another order of magnitude reduction maybe to get to a low TCE or vinyl chloride cleanup level, and we can rely then on this extended period of natural attenuation. And some of these papers talk about natural attenuation following bioremediation as enhanced natural attenuation. It's a term ENA that we can take advantage of. We also can take advantage of complementary and concurrent abiotic degradation along with our biological degradation. And we'll talk about this in the case study. The kind of redox conditions that we have to create for biodegradation is also conducive to formation of iron sulfide. So if we think about maybe injecting some extra iron or maybe both iron and sulfate together, we can get precipitation of very small iron sulfide crystals. So you look at these, this is called a framboid, this kind of circular arrangement of crystals, but these individual crystals are very small. What are we talking about? Like a half or less, maybe less than half a micron. And I think a human hair is 20 or 40 microns. So very small on individual, precipitate on individual aquifer grains, and they're highly reactive. So as groundwater moves through with TCE or PCE or even cis-DCE, it's degraded abiotically, it's degraded chemically, in addition to the anaerobic bioremediation that's happening at the same time. We'll talk a little bit more about that in the case study. And that can be accomplished through ferrous sulfate, or like a stronger, more robust abiotic treatment is through zero-valent iron. So now we'll launch into the case study, or I might just pause for just a second. Are there any questions on the primer before we kind of get into the specifics of the case study? All right, so this is a project that's been going on for a little while. I started with this project. Erin manages this project now. Going to give you kind of a general site explanation and talk about our approach, and then talk about the enhancements that we've done in addition to bio. So we've added abiotic enhancement. We've added some low temperature thermal to heat the aquifer up a bit so the bacteria perform better, and also the abiotic degradation performs better. And we've had to address some low pH conditions, and we'll show some plots that talk about how effective it's been. So general approach. Our approach here is to stimulate biodegradation through emulsified vegetable oil as an electron donor. And when we talk about emulsified vegetable oil, it's vegetable oil with surfactants, so that once it's mixed with water, it's like milk. It's not like you see individual droplets. The droplets are very small. They're submicron droplets, and it's mixed. And yeah, think about whole milk as being a sort of an analog for that. And then chemical degradation, we have used both ferrous sulfate and zero-valent iron at this site to stimulate the abiotic. Low temperature thermal is based on this Arrhenius equation, chemical reaction equation, that for every 10 degrees Celsius increase in temperature, you double biological and chemical reaction rates, degradation rates. And then we'll talk a bit about pH. The halicoides, all bacteria sort of have a healthy range of pH, commonly 6 to 8, but Dihalococoides is particularly sensitive. It really just won't, they will not work at all. They will not degrade contaminants at all below pH of 5.5. And we do have some pHs below that we've had to buffer. So this is our site, and I saw in the early, the slide that you guys deal a lot with kind of surface water concerns. You talk about that in this group, in this forum. And this is a groundwater problem, but groundwater at the site also becomes surface water because we have these two bounding creeks. And they actually pinch up, and there's a confluence of these two creeks a bit off of the figure. And so all the groundwater goes to these creeks. So our groundwater problem is a potential surface water problem. This is the highest concentration sort of chlorinated solvent site you can get. We're at the solubility limit for the chlorinated solvent. You can see that this plume, the dashed red line shows that we have a bifurcated plume. Part of the plume discharges to the North Creek and part to the South Creek just because we have a sort of a groundwater divide and flow in both directions. So this is me zoomed in on the source zone now. So these are all the wells within where the former vapor degreaser was that had a leak, and we defined our source as all the concentrations above 10,000 microgram per liter. Now, for context, commonly we will treat sites that have concentrations of 100 and 200 microgram per liter, and here we have concentrations that are, here's our maximum concentration at the solubility limit, which is 1,100 milligrams per liter, and the colored wells here all indicate that we had NAPL present, which is like pure phase TCE. So not just in the water, but like as a separate phase, a dense non-aqueous phase liquid. So pretty hammered here. And I'll switch now to a cross-section. You can see the cross-section alignment here right through the middle of the vapor degreaser. And you can see that, similarly, these green and purple and red indicate where we had NAPL. We were able to evaluate that and document it during drilling of these borings. And the NAPL extends really from groundwater table or even, right up to the bottom of the slab down to about 30 feet where we have this gravelly clay aquitard. If you guys are familiar with kind of Portland geology, this is the TGA. And sort of some intermixed layers of sort of aquitard clay material with, more sandy, gravelly alluvial aquifer. So when we apply bioremediation, this is a good example. It's not a rifle sort of precise application. It's a shotgun application. So we know, like, okay, we really got to flood this and get good treatment from the water table down to 30 feet or maybe even a bit below 30 feet where there's variation in this aquitard top elevation. And at this site, the aquitard is competent, and we have deeper wells that show us that we didn't get TC contamination into the deeper aquifer zones. So our approach here is a little bit of a variation on the basic concept of providing food to the bacteria. Yes, we're providing food to the bacteria, but we're providing an excess of vegetable oil here. Typically, we'd inject vegetable oil maybe at just 5% or 4% in a dilute solution to just feed them. But because we have such high concentrations here, we followed some, approach in the literature, which is to use higher concentrations and sequester mass in the source and allow treatment to occur there. So the idea is by having higher concentration of vegetable oil, we reduce the hydraulic conductivity of the source. And so more of the groundwater that's coming to the source moves around the source instead of through it. That reduces our contaminant flux to the down gradient plume. And the vegetable oil that we inject, these droplets become immobile in some short flow distance within 10, 30, 40, 50 feet of where we've injected them. And that oil droplet is a sponge for TCE. TCE that's in the water will partition preferentially to the oil, just like you think of TCE partitioning to a GAC, a granular activated carbon treatment system. It does the same thing with vegetable oil. And then as that droplet ferments over time and shrinks in size, it releases its TCE content into an environment that's optimal for reductive dechlorination and breakdown to end products. So again, just showing you what the baseline looks like. This is TCE to start with. And within 16 months, we were down in the down gradient plume. We were I think we had a maximum of about 7 in the down gradient plume. And that was all achieved through injection just in the source zone, but by cutting off that flux. And we also saw some evidence that treatment had extended, a couple hundred feet down gradient of where we'd injected it. The source was mostly addressed, and we could focus continued effort on the source zone where high concentrations remained. And that's really a good scenario where you don't have to go after active treatment in this larger plume. We're able to do treatment just at the fairly small source zone area. And this is a plot that shows an average for all of the wells in the down gradient plume. So everything down gradient of the source. And these vertical bars show the injections that we've done over the years in the source. And a couple takeaways here. This black line is total chlorinated ethene. So that's the sum of TCE, cis, and vinyl chloride summed and averaged for all of the down gradient wells in the plume. And you can see that decreased. So we term this total chlorinated ethenes. And what we don't want to see is that if TCE goes away, but the total chlorinated ethenes stay about the same, that just means we've converted it to cis or vinyl chloride, but haven't taken it completely through to end products. We want to be complete with the degradation products. So, first takeaway is that this total chlorinated ethenes has dropped off and stayed very low. And then you could see in these red bars is cis DCE. Cis DCE on a molar fraction basis was over 80% to start with, or after our first injection. 85% of the ethenes in the down gradient plume. And as time progressed, vinyl chloride sort of increased and then decreased, and then we became very quickly ethene and ethane predominant. Again, ethene and ethane are non-toxic end products. And so this whole period, the down gradient plume has been 70 to 85% of the ethene mass in that down gradient plume. So a very good result in the down gradient plume. But we still have this high concentration source zone that we can't ignore. We need to fully treat the source zone, or these gains that we've made in the down gradient plume would be lost because the plume would reestablish if we didn't fully address the source. So the source, bioremediation with abiotic enhancement. We've talked about this. This is the sequential biodegradation steps. By comparison, the abiotic pathways is really that you're degrading PC, TC, and cis to acetylene compounds and then to ethene, ethane. So you don't make any vinyl chloride. That's a nice benefit. Acetylene compounds are very labile. They're very reactive. So even at sites where we know this is occurring, often we don't see acetylene. But at this site, because our concentrations of chlorinateds were so high, we did see acetylene, and we were able to demonstrate, without doubt that this reaction was occurring. Now, an important thing to consider as we talk about acetylene going forward in this presentation is whatever you detect for acetylene is some small fraction of what has been produced because it's so quickly converted over to ethene and ethane. Okay, so just quick summary of what we've done. We've done, 7 injections over, almost 20 years. We've used a couple of different vegetable oil substrates over that time. Each has sort of some pros and cons. And it was here in the last 3 injections where we introduced ferrous sulfate and then colloidal ZVI to enhance this abiotic degradation as a complementary pathway. And then here at the very end, starting in 2002, where we introduced low temperature thermal and pH buffer that I'll talk about. And just to get a visual, this is what ferrous sulfate looks like on the left. It's sort of a brown water. As long as that tote stays anaerobic, the iron and the sulfate are totally dissolved. It injects like water. And then on the right-hand side is this colloidal ZVI, which is more like a black paint. It's about that same viscosity. Low temperature thermal. What you can see here, this is the source again, and the purple wells are 7 heater wells, and we monitor temperatures at these 2 blue thermocouple wells, and we monitor temperature at multiple depths. So for this specific For the dihalococoides to be most effective, it has an ideal temperature range of about 30 to 35 degrees C. So we were able to increase things from down around 20 to 25 up to 30 to 35. It would have had even a greater beneficial effect in a colder aquifer if baseline temperatures had been lower. But based on what we're seeing with temperature enhancement here, we should be having about a doubling of our degradation reactions. You see that the temperatures are a bit higher for this TMP probe. It's located closer than ideal to one of the heater wells, so we take those results with a bit of grain of salt, whereas the TMP one is located more midpoint between heater wells. And what you're seeing here is multiple depths through the aquifer from 5 foot to 30 foot. Excuse me. And then buffer treatment, we did have a number of wells that were below 5.5, as low as 5, or even maybe a little bit lower. And so in 2022, we didn't inject more food. We didn't inject more donor. It's the donor, it's the hydrogen that's produced that drives the low pH condition. It's also the dechlorination process itself, removing the chloride ions that results in a low pH condition. So we decided for this last injection, more food's not needed. What's really needed is buffer. So we injected buffer to all of the green wells here, 11 source wells where TC was still above 100. So some results here, the pH over time, and this is a messy plot to look at, but you can see this is where we started our thermal, and this is the August 22 injection where we did the buffering. And compared to baseline data, from back in 2004, that's not shown on this plot, we had no wells that were less than pH 5.5. So clearly we caused the pH problem through what we injected. We expected that we would, and now we're sort of dealing with it. Before we had the buffer, we had 12 wells. Immediately after we had the buffer, we had 9 wells that were still below 5.5. And then currently, which is, current is December 2023 here, a year after we did or a year and a half after we did the buffer, we had only 4 wells that were below pH 5.5. So a very good improvement, and we'll probably be looking at additional pH buffer there going forward. How effective was it? Okay, so every good scientist knows, I'm going to back up a step. Every good scientist knows that when you do an experiment, you should change one variable at a time. And here we changed, I think it's 4 variables at a time. So we're not very good scientists, but we're trying to be very good like remediation practitioners and efficient with our clients' resources and cleaning this up as quickly as we can. We'll parse out as best we can, like what the results tell us about which changes were most effective, but altogether we saw some very good effective changes. Bioremediation with these enhancements overall has resulted in an 88% reduction in the size of the source zone. So in 2005, the red was our 10,000 microgram per liter. 2003, we're down to 18. What is that? 12% of that. And at the same time, so this is sort of the outline, the 10,000 microgram per liter contour of our plume. If you look at the highest concentration core of the plume, wells that were above 100,000, you can see what it was in 2005 and then 2017. And then since 2023, all of our wells have been less than $100,000. So we're reducing the extent, we're reducing the concentration. And this is a similar plot to what we looked at in the down gradient plume. And again, this is an average for all of the source zone wells. And you can see that our total chlorinated solvents have come down over time, about a 50% reduction in total CVOCs through what we've done. We're not done yet. There's still, this would be a high concentration source at most sites. It's substantially reduced, but we're not done yet. And the average molar fraction is also very interesting to look at here. When we started, over 95% of the ethene molar fraction was TCE, and as time has progressed, cis DCE has become predominant. These are those red bars, and that's remained mostly predominant. And you can see here, particularly after we've made some of these enhancements, you can see that the vinyl chloride and the ethene and ethane have increased. We've also monitored acetylene, and we did have some acetylene concentrations when we were doing bioremediation only in the 6 to 24 microgram per liter range. Those approximately doubled when we started using ferrous sulfate with our vegetable oil injections, and increased by about 6 times once we went to some focused colloidal ZVI injections. And again, what we detect here is a fraction. It's not like you can do a mass balance and say, I have this much acetylene, therefore I've degraded this much TCE. It's some small fraction of what's been produced, but clearly a significant mechanism here. And just seeing it a different way, sort of in a map view. Before we used colloidal ZVI, we had pretty good coverage and maximum of 50 for acetylene. And then once we'd done the colloidal ZVI injections, we were seeing acetylene over a larger area and much higher concentrations, up to 300 microgram per liter. So we love that approach. We love to be able to, not just have one degradation pathway, but have multiple. This slide kind of focuses in on sort of that increase in vinyl chloride and ethene ethane. And so what we had before with all of this cis production and like very little vinyl chloride and ethene ethane, we would term like a cis-stall or a partial or mostly cis-stalled system. And it was primarily, we theorized it was primarily due to pH, the low pH. And as we buffered the pH, here's where the pH buffering happened between these monitoring events, and clearly we saw improvement in the vinyl chloride and the ethene ethane concentrations. There's still more to be done. I mean, what we want to get to is like these red bars go down to almost nothing, and we have vinyl chloride peak, and then we have ethene ethane, all that's left, and that's probably a few years, several years down the road. So some of you may have been looking and saying like, oh my gosh, this is taking a long time. How can this be an effective treatment if it's taken 20 years? Our mandate here, I should have indicated this at the beginning, this source zone is beneath an active manufacturing facility. So their job is to make money making parts. And our mandate was, whatever you're going to do, you have to minimize disruption to our production. We're not going to shut down. We can't shut down. In fact, whenever we did injections or even a lot of the monitoring, we're in there on a night shift to minimize our disruptions to the facility, because any disruption would be a huge cost, much greater than any sort of cleanup costs that we would incur. So over 20 years, yes, it's been a long time, but it's been a fairly minimal cost and very low disruption to the facility. We're in there injecting every 2 years to begin with, and then more recently we've injected every 4, or I think we're going on 5 years with the last injection interval. A little over $3 million to complete an RI, remedial investigation, feasibility study, risk assessment, do these interaction injections, 7 different injections, address soil vapor intrusion, that the volatile TCE and vinyl chloride was coming up through the building slab and getting into indoor air. So we've addressed that with like a soil vapor extraction system. The thermal design was a little bit expensive to install, but the power consumption is very low, less than $5,000 a year. So we kind of did a cost benefit analysis and said, if the adding the thermal will save us 1 injection and 4 years of monitoring, it's a win, and it should. It's going to double it will double our degradation rates, and should result in those kind of cost savings. So I do have some lessons learned that I could talk through, but I think I'll pause first and see if there's any questions before I keep yapping. Any questions on what we've talked about?
Well, thank you for the presentation. I do have a question. You mentioned before about how you went through like different types of vegetable oil, and I guess what were the pros and cons to each, and what made you decide to go with the one you ended up going with?
Yeah, perfect. So with a major consideration is always cost. So we had started out with a low cost vegetable oil, emulsified vegetable oil. It was pretty large droplet, which worked pretty well for us in what was mostly a sandy gravel aquifer. But we also found that as we injected it, the emulsion broke in the aquifer to the point that we would get several feet of vegetable oil accumulating in some of our wells. And that was interesting. We actually would sample that vegetable oil, and we found that we had, oh my gosh, I think it was like 10 or 15 times the concentration of our maximum concentration in groundwater we had 10 or 15 times that in the vegetable oil. So this idea that vegetable oil or the TCE partitions to vegetable oil, and of course any TCE napple that is contacted by the vegetable oil is dissolved into the vegetable oil. We had like proof positive of that. It was interesting. And we did remove some substantial mass by pumping out this accumulated vegetable oil from the wells. But it was a little bit of a hassle and it wasn't a huge benefit. And we found a better product down the road that was a mixture of emulsified vegetable oil and ethyl lactate. And the ethyl lactate is supposed to have a added benefit. It's an electron donor, but it also has an added benefit of being a surfactant to help us enhance the dissolution of the TCE in the aquifer. And so we switched to that, and that stayed better in emulsion. And since we've been using that, we've seen very little accumulation of vegetable oil in our wells. It's a bit more expensive, but it was sort of a trade-off there.
Yeah, that makes sense. Thank you. Does anyone else have any questions?
Well, I'll kind of launch into this lessons learned then, and we'll have a little more time after that probably for some questions. I don't know. We could spend 20 minutes on this slide alone, but I'll just kind of go through it pretty quick. Every site's different. There's different site constraints. There's different objectives. The contaminants are different. Maybe your aquifer is aerobic versus anaerobic. So everything is pretty custom tailored. You take lessons learned from other sites, but you do have to customize it. And we found that, yes, we can apply bioremediation to a super active, busy factory setting. We also have sites that are out in the woods, and we have to clear paths with a bulldozer to get to our injection wells and that sort of thing. So it can be applied in a number of settings with different constraints. When we apply bioremediation, we prime our client and the regulator to expect that the concentrations will go up, initially go up and then go down. Because we come in and we do all this injection, we disrupt the aquifer quite a bit, and so we enhance desorption. We're bringing mass out of the absorbed phase on the aquifer matrix into the aqueous phase. It's a good thing, but it can be a little bit of a shock to people to see like, concentrations went up by double in the groundwater samples. So you want to give people heads up about that. It wasn't clear 20 years ago that we could get complete reductive dechlorination from TCE through CIS to vinyl chloride to non-toxic end products. That's well established now, and we achieved that at all our sites. It also wasn't clear 20 years ago whether you could achieve the very low levels, MCLs, and that continues to be you can, but it continues to be a challenge. You don't typically do 2 to 4 years of injection and achieve MCLs for everything everywhere. You'll commonly have some vinyl chloride above 2, that has the lowest MCL. PC and TC have a cleanup level of 5. If you're looking at MCLs, cis-DC has a MCL of 70, and then vinyl chloride's lower at 2. So it's very common to have vinyl chloride be the last thing to clean up. It does clean up, but you may need to take advantage of this sort of enhanced natural attenuation period after your active treatment and expect a few years, 8 years, something like that to achieve vinyl chloride cleanup level. And of course, there's subsites in Washington where you wish you had the MCL of 2 microgram per liter as your vinyl chloride cleanup level. Instead, you might have 0.02. And then it's like, natural attenuation period will be essential to achieve that. Storm drains are not our friends. Wherever we inject, we expect that we'll have to plug storm drains, be very aware of injection fluid that might get into storm drains, and take measures to prevent it from getting into surface water. These are food-grade substrates, but they do carry a biological oxygen demand, so it's a sort of a moderate concern for discharge to surface water. And the thing I'll focus on here a little bit is, commonly when we're maybe the second or third consultant to a site, and we say, we think bioremediation will be a good approach, and they say, well, we've done it and it didn't work. And we say, well, let's see the details, and it turns out their volumes were much too small to be effective. And I'll show you, an example site here. This is a site down south end of Seattle, and these plus symbols are injection wells. We couldn't really locate them any closer because just site constraints. This is an active chemical distribution facility. We couldn't locate wells on 10-foot centers. I think these were like 35 feet apart. here's groundwater flow direction. We kind of want to inject two barriers and or two rows and have the groundwater carry our food, our electron donor down gradient and create overlapping treatment zones. And so we were competitively bidding for this work, and another consultant that also did bioremediation had said, "Yep, we'll do this, and this is the approach. We'll inject 2,000 gallons each." Well, if you do the math, of how far out, if you inject 2,000 gallons to each well, how far out does it push? And that's a pretty simple calculation: volume of a cylinder times some effective porosity number. And when you do that calculation for 2,000 gallons, these wells were screened, I think, 20 feet long. You get about a 4-foot ROI. And so when that happens, and you have all this blank space between the wells where you haven't distributed donor, you get striping. You get some effective treatment in a very narrow down gradient distribution, but not overall aquifer treatment. And so our approach was like 2,000 gallons, no way. We need like 30,000 gallons per well to get these overlapping and touching radii of injection. And then when groundwater moves that injected solution further down gradient, you have very good overlapping zones of treatment. And then you get results more like you were expecting or what you were wanting, right? You get some overall more comprehensive cleanup. And when we inject those large volumes, I mean, we're dealing with, often ganged, 6,500 gallon tanks, sometimes some 20,000 gallon tanks to mix our solutions in. And it's many sites where, we're not injecting one well at a time because that would take too long, but we're all set up to inject 6 or 7 wells at a time and monitor pressures and flow rates to each of the wells. And that's everything. Maybe there's some more questions, or maybe there aren't. Thanks for your attention.
Okay. That's, I think, all. Thank you so much for the presentation. This was all very interesting. And if anyone doesn't have any questions, I guess that is the meeting. But I will be sending an email out later today as well with just a form to fill out for this upcoming year EWRI meetings and just your feedback on what you would like to see. But thank you so much for coming.
Thank you for the invitation. Appreciate it.
Thanks, Clint.
Thank you.
Thank you. Bye.
Thank you.
Bye.
Bye.